Hello guys, welcome to Self-Help Maths Academy. Let's start with the examples now. Let me take whether the limit of these functions exist or not. If exist, we have to find them. So we'll start with this example, say limit of x into sine of 1 over x. So for a left hand limit, we will take this as limit x into sine 1 over x as x is tending to 0 minus 0. So this you know that when we are taking from left hand side, we'll take minus. So here what I will do, I will put wherever x is there as 0 minus h. So this will become now, as x is tending to 0, as x tends to 0, your h also tends to 0. By putting x equal to 0 here, we will get h as also tends to 0. Therefore, after changing the limits, we get limit as h tends to 0, replace x by 0 minus h. So it will be sine of 1 over 0 minus h. This is equal to limit of h tends to 0. This is negative h and this is sine of 1 over negative h. So this is equal to limit as h tends to 0. This is negative h into sine of negative 1 over h. We know that sine of negative theta is negative sine theta. So I'm going to substitute this value in this. So this is nothing but limit as h tends to 0. This is negative h here. So since sine of negative theta is negative sine theta, so I've taken negative out. This is sine theta here. This is equal to negative into negative, it is positive. So limit of h tends to 0, it is h into sine 1 over h. So now this is as h tends to 0, this value is what? It is 0. And this is into a finite value, because you know sine does not take any value other than negative 1 and positive 1, right? So it always, the quantity will be between 1 and negative 1. Okay, so therefore 0 into any finite quality between this 1 and negative 1, it is still what? It is 0. Okay, so this is your LHL. This is your LHL. Now let us find out the RHL. So for the RHL, what we do, we will start with limit x into sine 1 over x as x is tending to 0 plus 0. Now what we put here is, we will put x as 0 plus h. So this is equal to limit as h tends to 0. Now you see, I am changing as x tends to 0, your h also tends to 0. So change of limit leads to wherever x is there, I am putting h now. So it is x tends to 0. So here it is 0 plus h, and this is sine of 1 over 0 plus h. So this is simply limit as h tends to 0. This is h into sine 1 over h. So as you know, as h tends to 0, this is again 0 into sine of anything will be, it is a finite quantity which lies between minus 1 and plus 1. Okay, so it is always between 1 and minus 1. So now this is nothing but it also gives you what? A 0. So therefore this is your RHL. So from here, if you observe, this is your LHL which is 0. This is your RHL which is 0. So therefore, thus LHL and RHL both are existing. Both exist. RHL both exist. Okay, they exist and they are equal. And they are equal. So hence what? Hence limit as x is tending to 0, x into sine 1 over x, it exists and is equal to what? And equal to 0. Okay, and it is equal to 0. So this is how we'll be actually trying to solve the example. So now let me take another example where we will check whether the limit exists or not. So let me take another example. So here we have, say, f of x is equal to 2 to the power 1 over x minus 1. So for LHL, let us start with the LHL, left hand limit. So you know that it is nothing but f of 1 minus 0. So this is equal to limit of f of x as x is tending to 1 minus 0. Okay, so we are trying to understand this function as limit as x tends to 1. So therefore, I'm taking now 1 minus 0. So this will become limit as x is tending to 1 minus 0. This is 2 to the power 1 over x minus 1. Okay, so now what we understood from the previous. So here what for the left hand limit, I'm going to put my x as 1 minus h, because x is tending to 1, so it is from the left hand side, so therefore x will be equal to, x is equal to 1 minus h. So wherever x is there, let us put 1 minus h. So therefore limit, as you see, as x is tending to 0, as x is tending to as x is tending to 1, in this case we have to prove, right? They have given us to check whether limit of f of x as x is tending to 1 they given. So therefore as x is tending to 1, so put x equal to 1 in this. Therefore it will become what is h tends to, this will be 1 equal to 1 minus h, or h equal to 0. So therefore limit as h tends to 0, so this will be 2 to the power 1, x is 1 minus h minus 1. So this is minus 1 plus 1 cancels here, as h tends to 0, this is equal to limit as h tends to 0, 2 to the power minus 1 over h. So as h tends to 0, 1 over h, it tends to infinity. So since negative, so negative infinity, that is 2 to the power negative infinity, or 1 over 2 to the power infinity, because negative infinity means I can write this way. So 1 over anything like 1 over infinity is again still infinity, and 1 over infinity is what? It is a 0. So this is the value of the left hand limit. Now similarly for the right hand limit, okay, for the right hand limit, now what we do, for the given function, we will take limit f of x as x is tending to 1 plus 0. Okay, so this is like 1 upon 2 to the power x minus 1. So here we will put our x as, since it is a right hand limit, 1 plus h. Okay, so now wherever h is there, let us put that this is equal to limit as x is tending to 1, this value this value, if I take, this will be like 1. So 1 still cancels, it is h tends to 0. So therefore limit as h tends to 0. So it is 2 to the power 1 over x is 1 plus h minus 1. So therefore this minus 1 plus 1 cancels. So this is again limit as h tends to 0, 2 to the power 1 by h. So this will be 2 to the power infinity. Okay, 2 to the power infinity, which is infinity. Okay, anything to the power infinity is infinity. If you observe here, LHL is a it is existing, and it is 0, but RHL is infinity. So clearly your LHL is not equal to RHL. So hence the limit as 2 to the power 1 over x minus 1 as x is tending to infinity does not exist. It does not exist. So from this example, it is clear that though we have a LHL limit which is existing, RHL limit is infinity, and they are not equal. Hence, we conclude that the limit does not exist. Okay. So now let us see another example. Now we will see the examples where we will use the definition of epsilon and delta definition, like say using the definition. When I say definition, means it is epsilon and delta definition of the limit. We will prove some results. Okay, prove that. Let's see the first one. Limit of x square minus a square upon x minus a as x is tending to a is 2a. Let us prove this. So to prove this result, now we will start with, because it's the epsilon delta definition, so we will start with let here f of x is x square minus a square upon x minus a. Now if you observe carefully, limit of this function is equal to this, means this is your f of x and this is your L. Okay, and they have given that x is not equal to a. Here f of x is this function and x cannot be equal to a. So now we must show that by using the definition, we must show that, okay, for any epsilon greater than 0, there exists some delta greater than 0 such that the function f of x minus the limit value is 2a minus 2a. This is equal to, okay. Now what is f of x? It is x square minus a square upon x minus a minus 2a. Now let us take the LCM. LCM is x minus a. So this will become x square minus a square minus 2a into x minus a over x minus a. Okay. Now this is equal to. So let us further do the calculations. X square minus a square minus 2ax plus 2a square upon x minus a. So here we have x square and here minus a square and here it is plus a square. So I can write this as x square minus 2ax minus a square plus 2a square is plus a square upon x minus a. Okay. Now this is equal to. So this is like a square minus 2ab plus b square. So this is simply, I can write this as x minus a the whole square upon x minus a. So here 1x minus a, I can cancel with another 1x minus a. So this is simply modulus of x minus a. So therefore, modulus of f of x minus 2a, this is less than epsilon. This value is less than epsilon whenever 0 is less than x minus a, which is less than epsilon. Okay. So now we have concluded this. Okay. So we have got this value. Now we choose our delta as epsilon. Okay. Because in the place of delta, I have what? I have epsilon. So therefore, what I'll write? We are writing this as, say, delta is equal to epsilon. Okay. We are choosing our delta as epsilon. Hence, modulus of f of x minus 2a is less than epsilon whenever your 0 is less than x minus a, which is less than delta. So this is now like, it's a limit definition. So hence you can see this is f of x minus 2a is less than epsilon whenever this condition satisfies. But we started with f of x, which is x square minus a square upon x minus a. So this, therefore, what we can say? Therefore, we can say that limit of x square minus a square upon x minus a as x is tending to a is equal to 2a. Okay, so this satisfies the result. So this is very important. How do we prove that particular results? Now let me take another example where we will prove this with the definition. Let's say we have f of x as x into sine 1 over x. Okay. So here again, we'll start with, as you know that f of x is equal to x into sine of 1 over x is given. And now we need to start with, let us say, because as we don't have equal to something, so it is equal to 0. So therefore, what we will do just this way. We will take this as modulus of f of x minus 0. This can be written as x into sine 1 over x. This I can write it as a modulus of x into modulus of sine 1 over x. This is always, this quantity, for whatever the value of x, this quantity will be always lying between 1 and negative 1. Whether it is 1 or negative 1, modulus of this quantity will be 1 only. So therefore, 1 into this quantity will be what? Always less than or equal to modulus of x. Okay, so if you want to, you can write this as modulus of sine 1 over x will be equal to, it is less than or equal to 1. Okay, so now we have got an idea about this. This is equal to, now clearly, modulus of f of x, you see, minus 0. We got this as less than epsilon whenever your 0 is less than modulus of x, which is less than epsilon. Okay, by the definition of our limit. Now again I choose our delta as epsilon. So therefore, replace epsilon by delta. This implies modulus of f of x minus 0 is less than epsilon. This is true whenever 0 is less than modulus of x, which is less than delta. Okay, so hence what we conclude? Limit of x into sine 1 over x as x is tending to 0 is equal to 0 is equal to 0. Okay, this is what we have to say. Okay, so now this is another one. Now similarly the third one we have to show that limit of x square sine 1 over x as x is tending to 0 is equal to 0. Okay, to show this now, uh, again we will go with the same format as this one. So here we'll start with as it has to tends to 0, therefore let me take this as f of x function. The limit is 0 here, so f of x minus 0 is equal to modulus of x square sine 1 over x minus 0. Okay, this is nothing but what? This is nothing but I can write this as modulus of x square and modulus of sine 1 over x. Here still this sine 1 over x is between 1 and negative 1. Modulus of this function is still 1. So therefore this is less than or equal to modulus of x square. Okay, so this is now clearly we can write this as modulus of f of x minus 0 is less than epsilon whenever your 0 is less than modulus of x square and which is less than epsilon. So if I just take a square root, this is nothing but what? 0 is less than modulus of x which is less than square root of x epsilon. Okay, square root of epsilon. So now what I do, we choose delta as square root of epsilon. Okay, we choose our delta as square root of epsilon. Therefore modulus of f of x minus 0 is less than epsilon. This is true for 0 less than x modulus of x which is less than because I'm choosing my delta as I have a square root of epsilon as my delta, so this will be what? Less than delta. So this is nothing but what? It is the property of a limit, the definition of a limit. Hence we can say that limit of x square as x square sine 1 over x as x tends to 0 is what? 0. Okay, so here choosing epsilon and delta is very important. Okay, how do we choose and how do we go for it? Okay, now let us see. There is another example where let f of x is 1 over x, x is not equal to 0. Prove from definition of epsilon delta. Okay, epsilon delta definition, we need to prove limit of f of x as x is tending to say 2 is equal to 1 over 2. So this is what we have to prove. So they have given that this is a function f of x is 1 over x and x cannot be 0. We need to prove with the epsilon delta definition that this is equal to 1 over 2. To start with that, to start with the solution, to prove that limit of f of x as x is tending to 2 equal to 1 over 2, we have to show that for any epsilon greater than 0, we can find delta which is dependent on epsilon which is greater than 0 such that difference between f of x and the limit value, that is 1 over 2, this should be less than epsilon whenever your 0 is less than modulus of x minus 2 which is less than delta. So this is what we have to prove. Now what we do, we start with this. Now let us start with say modulus of f of x minus 1 over 2. So this we can write it as you know that f of x is what? 1 over x. So we can write this 1 over x minus 1 over 2. Taking the LCM, this will be 2 minus x upon 2x. Okay, so this we can write it as modulus of 2 minus x upon 2 into modulus of x. Now we choose our delta is less than or equal to 1. Okay, we are choosing our delta as less than or equal to 1 and your 0 is less than modulus of x minus 2 which is less than delta. Okay, so this implies since your modulus of x minus 2 is positive. Okay, so modulus of x minus 2 is positive, it is greater than 0, and modulus of x minus 2 is less than 1. So this value modulus of x minus 2 is less than 1, and we also from where we got this, because x tends to 2 means x minus 2. So that's from that definition we are taking it. 0 less than x minus 2. This is your x tends to 2 means x minus 2, which is less than delta. And since I've chosen my delta is less than or equal to 1, so therefore in place of delta I'm writing this as 1. Okay, less than 1. Okay, so that's how we have got this. So this implies x is greater than 0. That means x should be greater than 2. So x cannot be 2. X cannot be 2. And since you can see x minus 2 is less than 1, so here if you just put the values for x, so this values will be lying between, x will be lying between 1 and 3. X will be, because if you take plus 2, if you take minus 1, so this minus 2, I mean, like, if you add and if you subtract from both the side, you will get here 1 will be less than x, which is less than 3. Okay, so this is the result. And then as you know, we have both the conditions. So now let me do it simultaneously. So suppose as you choose your epsilon, you know that 0 is less than modulus of x minus 2, which is less than 1. Okay, so this we know, 0 is less than x minus 2, which is less than 1. Okay, so this implies modulus of x minus 2, either it is greater than 0, and modulus of x minus 2, either this is less than 1. Okay, this is what we know. Now this implies what we have said. This implies x cannot be 2, and your 2 minus 1 is less than x, which is less than 2 plus 1. So this implies what? Because it is x minus 2 is less than 1 means your whether the 2 minus 1 you take or 2 plus 1 take from left hand and the right hand, this becomes x cannot be 2, and your x lies between 1 and 3. It lies between 1 and 3. So this implies your x cannot be 2, and 1 is greater than, I'm just reversing the procedure, so 1 over, so this will become 1 over x, because 1 over 1 is 1, greater than 1 over x, which is greater than 1 over 3. So this implies x cannot be 2, and 1 over 3, this I'm taking it reverse, 1 over 3 is less than 1 over x, which is less than 1. Okay, so this is now an idea. So this implies what? X cannot be 2, and I just take a mod, so this will be 1 over mod x is less than 1. So therefore if I take this as 1, say from this as say 1, so from 1, if you see, this is like, okay, so here if you observe, it is 0, which is less than x minus 2, which is less than 1, implies your x minus 2 is greater than 0, and your x minus 2 is less than 1. So that's what we have got. Then from here, since it is greater than 0, so x cannot be 2, and since it is less than 1, so from both left and right we get 2 minus 1 is less than x, which is less than 2 plus 1. So from here again x is not equal to 2, 2 minus 1 is 1, less than x, which is less than 3. So this implies x cannot be 2, and so since if you take the 1 over, I mean, like reverse procedure, so 1 over 1 is greater than 1 over x, which is greater than 1 over 3. So this implies x cannot be 2, and your 1 over 3, I'm reversing now, 1 over 3 will be less than 1 over x, which is less than 1. So this implies what? X is not equal to 2, and your 1 over x is less than 1. Okay, so now you have taken this as if you see from here, we have taken this as equation 1. Okay, so what we will be doing is, now in this case now 1 over x is less than 1 we have. So here if you want, you can write, since 1 over x is greater than 1 over 3, 1 over x is greater than 1 over 3, which, and 1 over 3 is what? Strictly greater than 0. So therefore Therefore 1 over x is nothing but 1 upon modulus of x. So therefore we can just replace 1 x by modulus of x, because this value is still greater than 0. So you know that. Okay, so by the modulus of function. Now from the equation 1, from 1 we can write this as modulus of f of x minus 1 by 2. So from 1, modulus of f of x minus 1 by 2 is equal to so this one, this is like modulus of 2 minus x. Since it is a modulus function, I can write this as x minus 2 upon you see, this 2 minus x, we can write it as x minus 2, and also you can see the modulus of x, your modulus of x is less than 1, so therefore it is simply modulus of x minus 2 divided by I mean, like, since it is just changed, it is equal to 2 here, into 1 over modulus of x. I'm writing as it is. So this will be less than delta by 2, and this value is what? This value already we have seen, 1 over modulus of x, which is less than 1. So therefore let me write it as 1 here. So now let us choose a delta, okay, such that your delta by 2 is some epsilon. Okay, so if delta by 2 is epsilon, then therefore delta is equal to what? 2 epsilon. Okay, or you can say delta is less than so delta by 2 is less than epsilon, so therefore delta is less than 2 epsilon. Okay, also we have chosen our delta which is less than or equal to 1. All right, so therefore what I do, therefore we choose our delta is minimum. We choose our delta as the minimum of, because less than or equal to 1 means 1, and here our delta is what? 2 epsilon. So therefore we are just taking the minimum of these two, whether it is 1 or 2 epsilon, we take a minimum of these two. Therefore we have modulus of f of x minus 1 over 2. This function is less than delta by 2, which is less than, delta by 2 is less than epsilon, so therefore this is less than epsilon whenever 0 is less than modulus of x minus 2, which is less than delta. Okay, this is less than delta. So therefore by the limit epsilon delta definition, this quantity is less than epsilon whenever x minus 2 is less than delta. So this is like almost follows for both epsilon and delta. Hence what we can say, we say that limit of f of x as x is tending to 2 is equal to 1 over 2, is equal to 1 over 2. That is the important proof. Okay, this is like, this is how, if in the in some cases they will ask you to prove with the epsilon delta definition, how do we tackle with the different functions. As you see that they have given a functions and they ask you to prove that with the epsilon delta definition, prove that limit of a function is equal to 1 over 2. Now by looking at the problem, you may feel like, wherever x is there, we just put 2, then it will be easy. But no, we have to choose our epsilon and delta. Choosing epsilon and delta is very important in these type of examples. Okay, so once you choose your epsilon and delta properly, then only you will go further in order to achieve the final answer. All right, so this is all these are some of the examples which I have discussed now. So maybe some more examples I'll be discussing in the next video. Okay, so till then, take care guys.